Hello everyone, and welcome to our webinar on the latest advancements in DDR and LPDDR protocol analysis. We are excited to have participants from around the world joining us today. We will wait one more minute for others to join, and then we will get started. Welcome everyone. My name is Trisha, and I'll be your moderator for today's session. On the agenda today, we will have a 40-minute presentation, including a live demo, followed by a 15-minute Q&A session. Please note that all attendees are muted to ensure a smooth webinar experience. For those joining us for the first time, please let us a moment to provide a few quick guidance. For both desktop and mobile users, you will see a speech bubble icon with a question mark on the upper right side. If you have any questions during the webinar, please submit them there. We will answer questions at the end of the session. This webinar is being recorded, and the recording link will be shared with all attendees once it becomes available. Now the presentation will begin. Please welcome Dr. Mohamed Hafed, Founder and Chief Executive Officer of Interspec Technology.
Thank you, Trisha, and thank you everyone for attending this session with us. As Trisha mentioned, we will start with a short presentation followed by a live demo on a live PC. So I thought of starting by just describing the memory landscape today as we see it, both in the world of DDR and LPDDR. And one of the things that is very evident these days compared to decades ago is that there are so many more memory controller architectures in the world. Of course, there's the original x86 architectures, but then there's ARM that's very pervasive now, and then there are other applications like FPGA applications and proprietary applications. So more and more people are getting into the design of their own PHY and controller architectures. And more importantly, there are so many form factors that the industry has to deal with these days, right? And it just depends on what kind of innovation the end users are looking for. So in mobile form factors, for example, on the left, we see more and more co-package applications where an LPDDR memory would be integrated with a CPU in a single package. And what's interesting, as you can see in the picture in the left here, is that these are not necessarily bare die, known good die instantiations of the memory. They're actually standard package memories, but they're designed into a bigger package for the CPU. And then, of course, in terms of connectors themselves, even in the DDR5 world, you would see situations like DDR5 on a compression module as shown on the right-hand side here. You see a lot of LPDDR applications getting into not only laptops, but server boards as well. So the picture on the left is an example of an LPDDR5 LPCAM architecture where the standard package memory is integrated on top of a compression module that goes into the final form factor, like a laptop form factor, for example. And then, of course, last but not least, even in companies like Introspect, where we integrate memories into our test equipment, we would often use discrete package architectures. So this would be a simple an example architecture of discrete package placed directly on the board next to the CPU. And then finally, last but not least, of course, is the talk of the world right now is this LP SOCAM architecture, which is starting to become pervasive in server implementations. And so the picture in the background here is an incredibly complex application where you can see 4 different LPDDR rows of memories next to the CPU, and so the CPU has to talk to all of these at the same time. So this is really a big paradigm shift in how these memories are being integrated, especially into server boards. And so we're here to talk about debugging these applications and how to actually make sure systems work, where the problems come from. As as we state here, the problem statement is the more memories you have on a single board, the more interoperability challenges that you will face. And the interoperability challenges are basically associated with communications challenges, right? So different interpretations of the same specification, or simply bugs in implementing, the command sequences and the write and read sequences into the memory. So it's very difficult with a black box approach to understand where memory failures would occur, and that's really the problem we are trying to solve, is how to debug a live system to make sure that there are no issues with the protocol or no issues with the implementation of the JEDEC specifications. And so, of course, Introspect has been in the world of probing life systems for at least 10 years. We've been doing it in other applications, like in MIPI, for example, for image sensors and displays, or in DisplayPort, for example, embedded DisplayPort, where this is a laptop that's running live, live Windows operating system, and the Introspect is being used to probe it using a 2-piece architecture that we will get into a bit more detail later. One is what we call a remote sampling head, or an active probe solution, basically, and then the second piece of the solution is a protocol analyzer. So we're here to talk about this for DDR and LPDDR applications. So as we said, the concept for analyzing a live system is illustrated in this slide. And the key is that the tester itself, the instrument, is neither a source nor a sink. It's really just passively listening to the traffic. And one of the design philosophies, or the test philosophies, that we have adopted here at Introspect is that we believe that it's best to use active probe technology so that we don't degrade the signals as they propagate through. So the recommended solution for probing a live LPDDR or DDR system would look like the block diagram shown here, and consists of 3 pieces basically. One is the interposer, which is really the sensing part, the part that senses the signals going between the memory controller and the memory without disturbing them. And then these sensed signals go into the RSH, or the active probe amplifier, and then the output of the active probe amplifier goes to the protocol analyzer. And so this architecture might be a bit different from what you've seen in the old days with the logic analyzer architectures, but that's just the result of the engineering requirement, right? The data rates are a lot higher now. The voltages are a lot lower because you're getting LPDDR signals into very noisy server applications. And so you need a pristine signal integrity solution like this. One of the big advantages of this architecture, actually, as we might show you later in this presentation, is that the active probe solution basically is compatible with any oscilloscope. So that same setup where you've place the interposer, place the memory into it, and then connect the active probe to it, that same setup can be just carted into an oscilloscope where you see a signal on the scope, or carted into the logic analyzer or the protocol analyzer, where you actually get the design validation, the full protocol capture on all CA and all DQ channels. And so in terms of what the analyzer can do now, right, what do you get out of an analyzer that you do not get out of a scope? And the first thing, of course, is you get the what we call aligned parallel capture, right? So if you connect, let's say, a CA bus and then 2 bytes of DQ to the analyzer, then you'll get all signals traced in parallel and with automatic phase matching on all signals, right? So fundamentally, at the lowest level, the protocol analyzer is essentially a logic analyzer. It will just detect edges and it will display them and will give you the exact timing at which they appear. So if there's any timing mismatch, like where my mouse is pointing here, you would actually see them. So that's fundamentally what the protocol analyzer is. But of course, as engineers and as humans, we want to get more rapid insight a lot more quickly than just looking at logic waveforms. And so what we have done at Introspect is we have created a high-level protocol analysis layer on top of it. And so this is why we call it a protocol analyzer and not a logic analyzer. So every trace that is captured in this system, through the interposer and the active probe and the analyzer, essentially gets converted eventually into a table like we are showing here, where you get a human readable representation of the commands, right? So activate commands, read commands, write commands, and so on. All of these are represented here. And as I will show you later in the demo part of this webinar, you get hyperlinks. You get hyperlinks to go between the logic view and the protocol view, as well as getting information about the arguments for commands and so on. So the intent is really to increase productivity by giving you as much information about the protocol that's being transmitted as possible without you having to go and analyze the timing diagrams yourself. And then on top of that, of course, since this is a design validation tool and a tool to help find subtle bugs, what we look for after decoding the commands is then measuring the timings between commands. And so in the table view, as we'll show in the demo later, every entry in the table will get a specification window like I'm showing here with my mouse, where you get all relevant timings related to that specific command. And then you also get warnings about violations. So the particular command that we are looking at here is shown here. That's the truth table for it, and these are the arguments for it. And then the specification window at the bottom here is basically giving us the list of timing specifications that are relevant to this command. And we see here in the second row that the pre-charge command essentially seems to be off. What the analyzer measured is that the distance between our current command, which is command number 121, and the next pre-charge, which is command number 32, happened to be 39 NCK cycles, whereas the specification asks for 49 NCK, right? So this would be a warning that is specified here. And then all these warnings are collected and and displayed at the end. And as we will see with the live demo today, it's just incredible how many of these timing warnings we see and how consistent they are for a specific implementation, like a specific implementation. Let's say if it's off by 10 NCK here, like this one, every time a command like this comes, it will be off by 10 NCK with respect to the pre-charge command, right? And so these are consistent design. They seem to be consistent design errors, or perhaps they're conscious design decisions, but nonetheless, they are violations of the JEDEC specifications. And then, of course, one of the big features for this particular tool and why we went with the high-level protocol decoding is tracking of mode register read and write operations. So this is something that's very important for Introspect because we believe in actually getting traces that can actually then be converted to be played on testers for failure analysis, let's say. So we've invested quite a bit of effort in tracking mode register commands and decoding them. So this is useful for the engineer live when they're looking at it. For example, a frequency set point change on LPDDR, you'll be able to see the register bit fields for the frequency set point change, and then you'll be able to see if the frequency changed or not. But like I said, for us, a lot more important than that is to actually take that entire trace and see if you can convert it into a vector file that you can play on ATE, right? And then you can do real failure analysis with realistic payloads. We've had cases where we would like maybe take 100 milliseconds of traffic from a smartphone and then convert that into a vector and try to play it on an ATE, right? And so this gives us the ability to do, failure analysis with more realistic and with real system traces that we've got from a failing device. And then I think the topic of clock change is something that we have discovered over the years. We started developing these solutions maybe 4 years ago, and we were as we started getting into the implementations, we realized, especially for LPDDR, more so than DDR, no real system will run at a constant frequency, right? So especially smartphones, you'll have frequency changes. As we are showing here, you'll have frequency stops as well that I'll get into the next slide. And these are typically very difficult for test equipment to track, right? And so we've designed the architecture of this protocol analyzer from the get-go to try and catch what we call instantaneous frequency changes. So in this particular trace, on the left, we have the human readable section of the table, and on the right, we have the logic waveform, right? And so here in the human readable table, you can see that the CA bus was running at 600 megabits per second initially, and then it flipped to about 1 gigabit per second for the CA bus, right? And so these are just the FS frequency set points that the LPDDR spec specifies essentially, and this particular boot up sequence is showing us that the phone had gone from cold boot to the first frequency set point, second frequency set point, and so on. So the analyzer was able to track it here in human readable form, and then in the logic waveform, you can see on the right the actual signals. So the CK signal was relatively slow here, and then it doubled its frequency right on the fly, and you can see within just a very few clock ticks, you see the power down exit command, or some kind of command at least, that's being sent here right after the frequency change. Clock stops are even more jarring for equipment, and this is an example of a real form factor. I think it might be a smartphone form factor, where you see the analyzer basically goes from tracking the original clock frequency on the left, and the command that is here is a power down entry command. So we see the chip selects and the CA lines representing the power down entry command, and then the clock goes completely dead for a while, and you can see 2.2 milliseconds of stop clock in this case. And then when the clock starts, within a few clock cycles, the PDX command starts to appear right away. So this kind of capability is necessary if you're debugging a live phone in particular, or mobile applications where power savings are important. And we've seen cases, for example, where we would measure a phone when it's running on battery versus when it's running on a power charger, when it's plugged in, and how the power down statistics appear, right? And even when the battery discharges to lower and lower energy levels, you'll see a lot more power down entries happening in the protocol. So you can see what the operating system is doing in relation to the battery charge or the condition of the battery, at least in general, in these applications. And then, of course, being an analyzer, you need to trigger on commands. So this particular tool basically decodes the CA bus and the chip select signals in hardware. And what that does is it allows us basically to trigger on specific commands, or to even create custom commands. So in any introspect analyzer, whether it's for DDR or other applications like MIPI or DisplayPort, what we always have is a real state machine, like listening to the traffic that's coming in, and a data capture that we display in the viewer is really nothing but just a frozen snapshot of the traffic in time, right? And so this allows us to do custom triggers, like I said, but it also allows us to do, to give you insights into traffic before the trigger, like a pre-trigger window where you see what happened before the trigger, and then you get information about what happened after the trigger, and then you can decide also how to stop a capture, whether to stop based on a number of commands or whether to stop based on some other command that you have received. And so before going to the demo, I mentioned the interposer at the beginning and the active probe. This is something that's relatively new for the DDR community, I guess, when it comes to logic analyzers. So we will spend a few minutes describing this solution. And so Introspect has been making active probes for the last maybe 8 or 9 years by now. And we started doing it by creating individual scope probes like what I'm showing here. Everyone has used oscilloscope probes, and so you can see the anatomy in general is basically a tip of some sort that gets soldered into the form factor that you're measuring. The tip will typically have an SMPM connector, let's say, that goes into the probe amplifier. So this is really the main part of the active probe. And then the output of the active probe would go to an instrument like an oscilloscope or a protocol analyzer. And so for wide bus applications, we just wanted to create a more clean environment. We used to just put 10 or 12 of these next to each other, and it would look like a very messy bench environment for our customers. So based on feedback from our customers, we decided to create the RSH. And in one statement, the RSH is basically nothing but 12 active probes integrated into a box and shielded with metal all around it so that it gives a very clean noise environment. So this is really what the RSH box is just a set of 12 active probes in monolithic form factor, just designed within a chassis and shielded so that it can give the best signal integrity. And when coming up with this architecture, we thought about the number of probes to integrate in an RSH for a long time. And for memory applications, whether it's LPDDR or DDR or even Gen 6, LPDDR6 and DDR6, we found that the sweet spot would be 12 probes per box, so that you can maybe get some channel CA channels on an RSH, some other DQ channels on another RSH, like a 1 DQ byte per RSH, for example, and so on. So the number of probes in an RSH is somewhat arbitrary, but this is what the architecture that we came up was. And so just to drive home the message again more clearly, if I just do a quick animation of how the RSH is constructed, we start with the anatomy of an individual probe, and then I mentioned the solder tip, the tip attachment mechanism, the amplifier itself, and then how to connect to an instrument. And so the first thing we did was we basically said there's going to be 12 tips now connected to the single probe amplifier. So we, instead of the single SMPM connector, we have, figuratively speaking, the 12 SMPM connectors shown in this adapter here, right? So this would be one part where the tip attaches to the probe amplifier. And then instead of the individual probe amplifier, we have this box now that has the 12 probe amplifiers inside it. And then since there are 12 coaxial cables coming out of the probes, then we have decided to go with a multi-coax solution like the one we're showing here, where you have 12 outputs going to the scope or to the protocol analyzer. So the point is, this is really a conventional oscilloscope probe. You can literally take any one of these cables and connect them to the scope and you'll see your signals. But we've compacted the form factor so that we can measure more signals simultaneously and connect them to a protocol analyzer. And so last, of course, is the interposer itself, right? Because this is the big part of the puzzle. And this is something, again, that we have studied for a long time at Introspect. And we have looked at, conventional interposers with the LPDDR and DDR applications. And the thing about these applications is this, they are standard packages for sure, which is good. So it means you can buy interposers from third-party vendors, or you can create standard interposers. But the large number of channels makes it very, very unwieldy sometimes. So for example, what you have to do if you have to probe an LPDDR package on a live form factor is you'd create an interposer like we're showing here in the purple block. But because of the number of channels and because the scope probes are third-party probes that get attached outside of the interposer, you'll end up with stubs like the yellow trace that I'm showing here. So this is just necessity of routing a few millimeters through the BGA array out to the solder point for the active probe. And to add jeopardy to this is that the active probe is itself high impedance. And as I will describe later, a lot of the LPDDR applications are now running in unterminated mode. So when you have high impedance, when you have a long stub followed by a high impedance probe here, and your memory is running in unterminated mode, that's just a recipe for completely closed eyes, essentially at the speeds that we are looking at. So at Introspect, we decided to take a different approach. And what we really did in a nutshell is decided to make the interposer part of the probe amplifier. So if you remember my animation I had before where you had the cable going to the tip, Now we're saying that the interposer itself is the tip of the probe amplifier, and it's just a multi-channel tip of the probe amplifier, which means that the tip resistors, where the cables actually go and tap the signal under test, they go under the BGA array itself and not necessarily on the periphery of the BGA, and that eliminates the few millimeters of stub that I just showed you earlier. So if we go to the same animation that I had before, instead of having the solder tip on the edge of the memory package, where you inevitably will have to suffer with a few millimeters of trace to the BGA under interest, we basically said that the interposer itself is the tip. So you really have to design the interposer as part of the amplifier solution. And each ball that we're sensing, let's say there's let's say a CA bus and 2 DQ bytes, let's say 32 signals that are being sensed under this interposer, then the tapping point under each of these 32 balls basically is under them. And then you have just a controlled impedance trace going all the way out to the probe amplifier. So it looks a bit different, but it does give you the advantage of lower noise and higher signal integrity. So here's an example of a live phone, as you can see. So this is a live Samsung phone, and this is a package on package application. So the memory is where I'm pointing with my mouse here. And normally, without the interposer, it would be sitting on top of the package, let's say a Snapdragon package from Qualcomm, for example. So for this kind of debugging, we basically removed the memory from the package, and then we installed the introspect interposer, which is the blue PCB here, and then put the memory back on. But you can see that the interface to the oscilloscope or to the to the active probe solution is no longer a soldered down tip. It's just a microcoaxial cable. It's a controlled impedance microcoaxial cable that gets connected to the interposer through a connector. And we can get away with doing that because the resistors, like I said, are underneath the memory and not at the edge. So we eliminate the soldering part. You still solder the interposer, which is necessary, I guess, in general, but then you eliminate having to solder probes on the interposer. You just simply connect the microcoax cable assemblies into the interposer. And because the active probe has so many channels on the back, again, you can connect the entire CA bus like we're showing here. This is connected all the time, right? And it depends on which signal out of the RSH you use to view on the scope. You can just take it and view any signal that you want on the scope. So we've moved the problem from soldering tips onto the interposer to just taking the output of the probes, which is already always there, and just connecting it on the scope or the logic analyzer. So what this gives us is two things, like I said. One is noise. So this is a particular example where we've just left the system running for overnight, so for 26 hours. And this is on the scope. So this is the active probe output from introspect going to the scope. And you can see what we're trying to show here is that there's no EMI bursts or Wi-Fi bursts or RF bursts that create a green band of signal around the eye that just makes it very difficult to measure anything. And then on the other side, here's an example of an LPDDR5 application. That's a DQ signal running at 6.4 gigabits per second, and that's the read response coming from the chip. So this is basically what the chip is producing because we're sensing right underneath the chip and we're taking it out to the scope. And so you can see there's not much reflection going on here with this particular interposer. And so at this point, I'll summarize this section of the webinar, and then we'll switch over to the demo after that. So in summary, basically, we have focused today on enabling debugging of live systems that include LPDDR and DDR applications in particular. And so this is really the key is how can you run them at speed and then still debug them and decode the protocol. And then the second bullet here basically summarizes the two key points that we wanted to convey in this webinar. One is that the analyzer has to have a high sampling rate, of course, to be able to track all these high data rates and also all the instantaneous clock frequency changes. And then the interposers themselves have to have high signal integrity. And hopefully I've shown you that with the slides. And now I will move over to the live setup with a small PC and then show it to you operating live. So here is a live PC that is based on the Windows operating system and whose architecture is built around LPDDR5 memory. So as you can see, this is a live Windows operating system. We can run any application we want here. But what's special about this particular PC is that we are probing it live with the introspect LPDDR protocol analyzer. So I'm showing the logic board for the PC here. And of course, of particular interest is the LPDDR5 memory. This is a 315 ball standard package of DDR5 memory. And here it is sitting on top of the introspective technology integrated tip interposer. This kind of interposer provides solderless access to all signals under the memory. So here we're showing the DQ signals in this green cable assembly and the ACA signals in the blue cable assembly. And because it does not require any soldering and everything is embedded inside the connector, you get very high signal integrity and very low noise coming out of this interposer. The signals coming out of the interposer are going to two RSH devices. These are remote sampling heads, and they are active probe solutions that provide access to 12 channels simultaneously. In this particular demo, we're showing two of them. One, like I said, is connected to the DQ bus on the green assembly, and the other is connected to the CA bus on the blue cable assembly. The output of the RSH is just like any active probe solution, so it can go to an oscilloscope, or it can go to the Introspect Technology M7030 DDR LPDDR protocol analyzer. This is the latest product from Introspect Technology, and it addresses the highest speed applications for memories with a high sampling rate, with advanced features like supporting clock stops and clock frequency changes, and unterminated CA operation, as well as nested triggers and nested commands for different applications. So now we have moved to my PC where I have Pine3 open here. And by way of introduction for Pine3, of course, it's our development environment that works with all of Introspect's test equipment. And fundamentally, it's a Python interpreter. So the main window here is a Python editor where you can enter any Python command, including if and for statements and dictionaries and so on. And so what we have done at Introspect is we have created Python classes that represent the hardware, that represent the analyzer that you are using. And in this particular case, one class is called the analyzer calibration class, and another class is called the data capture. These classes have methods associated with them, just like the run method that I'm showing here. They also have attributes or properties that you can assign. And so in this case, I'm assigning a result name called test tiny PC. These attributes are available through Python, but they're also, for the most part, available in the GUI through this pane that I just opened right here. So you can imagine the attributes for the capture component, including things like the receiver channel list. So this is the list of channels that you want to probe, basically, with your analyzer. And as a convenience method, we have created a component class called DDR channel labeling that maps basically the interposer signals to the analyzer pinout. So if you look at this table, for example, here, the signal CK is connected to channel 5 on the analyzer, the signal chip select 0 is connected to channel 4, and so on. So once you have these labeling components available, you do not have to worry about pin position on the analyzer. You just worry about the signal names which are coming from your package and your protocol. What's more actually is that the interposers, with the standard interposers that Introspect has created, you can also have pre-populated channel labeling components like this, so that you can just reference the interposer and you'll know that the pinout on the analyzer is already pre-configured for you. There are other attributes in the data capture component, for example, like trigger options, where you can trigger on different commands. You can trigger on sequences of commands, or you can even trigger on custom commands where you create your own truth table combination and you ask the analyzer to trigger on it. For now, I will leave everything as default, and then I will do a quick run on the analyzer to see what that PC is doing. So the capture has already ended, and now in my result icon here, I have a notification saying there's a new result. I will click on it and open the viewer, and then here we see now basically what the PC is doing. What we have done to enable this application is since it's a Windows application, we wrote a small script on it to do a bit of a stress test on the memory. And so you'll see a lot of write commands, you'll see a lot of read commands, and that's just to stress the memory and take it through its paces. So you can see the memory is running at 5.2 gigabits per second in this case, and you see every command that's being sent. So activate commands are visible, write commands are visible, and then at the top, I think I've shown you some read commands, recharge commands available here as well. And so every time we click on a command, we would see the arguments associated with that command available in the row that we have highlighted. But also on the left, we can see also the arguments in the table that's listed on the left-hand side here. So the analyzer basically decodes the truth table and gives you a human readable way of understanding what commands are being sent. And then at the bottom left here, you will see a timing analysis basically to tell you if something is in violation or not. And so if we go to the top here, I think there was already a couple of warnings where things seem to be a bit too close. So for example, this particular write 32 command, there is a warning where the spacing to the next read 32 is a bit too close. So command number 12, which is read 32 here, comes after 40 NCK instead of 42 NCK as defined by the specification. So this would be a real violation that we have observed here. I can go to the waveform for the write 32 and just like try to observe what really has happened here. So this is my write 32 edge, and then if I just keep zooming out, without losing my bearing here, you'll see that the right 32 edge that I had was somewhere here as identified by these faint gray markers. And then the timing that under issue here is the second read 32 command seems to be too early, right? And so this is just the analyzer counting the number of CK cycles between these two commands and saying that there could be a timing violation here. And so this was just a quick view of how a capture is run. If I close this and run another time, it will show you this concept of scripting, right? So every time I click run, the script is executed again the same way, and I will get a new result object here, and I will open it. And you'll notice that the trace now starts differently because in my trigger options, I haven't really declared anything, which means I'm just going to trigger on any chip select that I see. If I trigger specifically on a P-charge, let's say, or on an activate one command, then I will always see the beginning of the trace being the trigger command that I asked for. And the reason is that the analyzer is always actually monitoring the traffic in hardware and understanding the commands that are coming in. And when you trigger on a certain command, the analyzer just freezes that capture window around the command that it sees. So there is hardware processing that is happening here. And what the viewer is giving us is basically just a snapshot of the traffic that's been received by the analyzer. So in this case, again, we're seeing a section of write and write operations. I click on the activate command just to show it. For those of you who are familiar with the activate command, this is very evident here in this waveform. But I'll also go to maybe show you some of the DQ lines. So I'll add a couple of DQ lines to this particular trace, just to show again the traffic. And so you can see now the DQ is running at the speed of WCK, so it's very fast, and that's the biggest advantage of this analyzer, is that its sampling rate is so high that it can capture DQ on LPDDR5 and even LPDDR6 applications. And then finally, something that I haven't showed you in the last run is this analysis tab, where you get statistics of the commands that you have received with the analyzer, as well as timing histograms as well for the different timing parameters that have been analyzed by the tool. So this is where a lot of the analysis, your analysis happens. You want to know what your system is doing and what your controller is doing to the memory essentially. So all of these timings are measured and displayed. They are displayed here graphically, but of course they're also available in Python, and they're also available in the file system as files, in either JSON files or raw files that you can retrieve and analyze yourself. And again, as mentioned, most of the traffic here is write traffic. That's just by virtue of the stress test that we've created. And you can see the different rank operations as well. So with this, we will conclude the demo and also conclude this session.
We will now begin our Q&A session. We already have several questions, and if you have any additional questions, please type them in the questions section, a speech bubble icon with a question mark on the upper right side of your webinar menu.
Okay, so I'm just going to process the questions as I see them. So first question is, can it support DDR? Yes. So this the demo I showed you was LPDDR, but the DDR truth table and decoding and everything is all included, and there's no license fee or anything like that. So every time we add a protocol, it will be just included in that. Another question, what is the maximum speed that you can measure? So right now, this particular instrument is rated to measure 20 giga transfer per second memory interfaces. So it's really designed to go after the DDR6 and LPDDR6 paradigms. We're looking to increase that rate over time, but this is what it's specified at today. What is the capture depth of the data capture without trigger options? So in typical payload traffic conditions, we have seen, like I said, maybe 100 million NCK cycles or 200 million NCK cycles. There's a bit of overhead that happens when we measure signals. So that's what I said. That's why I said it's based on the traffic payload, whether it's high density traffic or low density traffic. But in general, there's about I think 1 or 2 gigabytes of storage per channel on the analyzer, and there's also a lot of deselect filtering. So this is why we can capture, let's say, 100 milliseconds of trace on a live form factor like a live PC or a live smartphone. What is the underlying technology? Is it an FPGA? Is Nyquist criteria for sampling really achieved for high speed grades? So it's a custom designed analyzer from scratch. Of course, there's an FPGA in there, of course, but the active probes is one thing, and then the analog front end is our own custom analog front end. And inside there's basically custom circuitry for source synchronous tracking and capturing the signals so that we can, get all the CA and the DQ signals relative to either the CK or the WCK. So it's really a proprietary solution. It's not an FPGA solution. What is the maximum speed supported for DDR and LP5 currently? So we already answered that. So basically, I've seen you trace. The traces I've shown you on the PC are 5.2 gigabits per second on the PC. On phones, we've seen 8533. On customer labs, we're at 9.6 and 10.6. The analyzer itself and how we tested it internally with our own tooling can capture 20 gigabits per second, whatever the protocol. 20 gigabaud per second, actually. Does the timing analysis window show histogram for different frequencies separately? That's a good question. Right now, it's for one frequency, but we will ask the software team to separate it based on frequency. I mean, you saw I already separated it based on rank, so it's very easy for the team to also separate it based on frequency. Do you have custom-made interposer to support different board design? Yes. So for each package, let's say it's a 496 package, LPDDR5, or the new LPDDR6 357 package, typically we will start with what we know about the world. So for example, LP-SOCAM now is so important. So we know the constraints for LP-SOCAM. So our first design for the LPDDR6 357 ball package fits within the LP-SOCAM. But we know that your form factor might always be different, or you might have inductors or power components and stuff like that. So we do have a service to retarget our layout to your custom board specification. That's usually at a very rapid turnaround, like maybe within a couple of weeks to redo the layout and then fabricate again. In general, we are able to redesign the interposer based on your mechanical constraints. And we do publish our mechanical design information for our existing interposers. So we have a catalog of available interposers with their mechanical files. If you like them, you can buy them as they are. If you don't like them, we will redesign them for you. What is currently the biggest challenge in maintaining signal integrity during real-time probe and analysis? It's a good question. I think we have, at the way the interposers have been designed, we believe that the return loss topic is largely under control. In other words, reflections and stuff like that, these are largely under control. The next one becomes noise environments within the systems. So the systems are very, very, very noisy, and like we even wonder if they even pass the JEDEC specifications or not, because they seem to be very, very noisy. So that's typically the biggest challenge, is how to make sure that the interposer is installed properly, how to make sure that there's no other sources of noise that are coming in. What other footprints do you have available, and how to connect the interposer on complex small space, example RDIMM? Yes, so we do have RDIMM form factor, so like an RDIMM riser solution. Let me actually take a picture of it here and show you. So these are examples of the form factors. Like I said, we're now into the tens of form factors for them. But for the riser, for the RDIMM, on the right-hand side, this is our RDIMM riser solution, and this is currently, we boot up DIMMs at 10 gigabits per second with this, so it does pass the signal integrity check from from an eye margin point of view on the system side. And also, of course, the probing is still using the integrated tip interposer. So there's really just a high impedance tap coming into this microcoax cable. So the signal integrity in terms of reflections, especially from right side commands, let's say from the CA and the DQ from the phi side driving into the memory. That's generally very, very clean. But this is what we're using for high-speed debugging for both the RCD or for a complete RDIMM or MRDIMM. What is the difference between RSH3 and RSH2? It's a bandwidth. So RSH3 is our latest active probe solution. It's not on the website yet, but it's shipping as of this month, and that has an analog bandwidth that's up to 35 gigahertz. So this is really getting into the territory of the most expensive scope probes that you'll find on the market right now. But it still has 12 channels in there, and so it can connect to a scope or it can connect to the introspect analyzer. Whereas the RSH2 is still in the 10 gigahertz kind of range in terms of bandwidth. So it might sound small, but it can still capture the CA on a lot of the DDR5 and the LPDDR5 applications. Do you support other termination modes for the RSH, like active termination? Yeah, that's a good question. So especially on the riser here, so especially for DDR, where the termination is up instead of down. So the circuit, and there's even some, you can see some regulator circuits here. So there's some circuits here to create a termination level so that the tip is terminating to like 1.1 volt instead of 0. But keep in mind that these tips are high impedance tips, right? So they're really like 1K and above impedance. So they do not load down your DDR bus. This is not a passive, just a resistor divider and that's it. This is really a high impedance tip. So the amount of loading on your DDR5 bus is very, very low. Like when we look at the return loss when the tip is attached versus when it's not attached, it's within a few, like only a couple of ohms away from the nominal impedance of the trace. Could the same protocol analyzer features be used with the SV7C? So the short answer is yes, up to the speed capability of the SV7C. So a big difference between the SV7C and the M7030, or what we call internally the SV7C Plus, is that the sampling rate is at least 4, if not 5 times higher on the M7030, right? So this allows us to get into the LPDDR6 and DDR6 regimes. But let's say you're an LPDDR5 and you're looking only at the CA bus, then the SV7C can have the exact same GUI that we showed you, the same interposer, the same RSH, and you'll be able to do a lot with the CA bus. I'm just waiting here to see if there are any more questions from Trisha as she types them in. Okay. So it sounds like there are no more questions. I wanted to thank everyone again for attendance and for the engagement. Actually, I see a question. Okay. How does the signal voltage sampling been ensured here for proper protocol capturing? Like the regular LA, do we need to adjust it in order to get a proper sampling? Yeah, okay, so the question, again, I will read it out loud. How does the signal voltage sampling been ensured for proper protocol capturing? Like in the regular LA, do we have to adjust it in order to get proper waves and proper sampling? So yes, if you noticed in the demo, there was a component called analyzer calibration. Typically, it does it all automatically. So if you have traffic running on your system, so the only requirement is you need to have traffic running in your system, then the analyzer will sweep its VREF, like its reference voltage, very much like the receiver, right? So it will sweep the reference voltage to center the range of the eye. So then it will it will center the range of the eye. And then in the phase domain for the sampling, it will look for specific signatures, especially on DDR and LPDDR as opposed to GDDR, for example. You have the chip select and you have the CK and you have the WCK, right? So it will look for these edges and try to calibrate delays against them to make sure that it can get proper CA decoding relative to those edges. So it tries in the phase domain, it measures relative to the clock edges, and in the VREF domain, it tries to calibrate by sweeping up and down its own VREF to find the center of the eye. And then it will give you a set of calibration values that are stored in a file, and you can adjust them if you don't like them. You can adjust the file and use those same training values. Okay, I think we're close to the end of the session as it is already. So thank you again for attending. And thank you very much for the engagement and the amount of questions that we have received.
Okay, we will conclude our Q&A session. And if you have any questions regarding this webinar, please contact us at info@introspect.ca. And thank you all for joining us today. As we announced earlier, we will be including the link to the recording of this webinar in our follow-up email. Before we end, I want to take the opportunity to share our upcoming complimentary webinar on the new feature of our Pine Tree software, Signal Integrity Simulation, on July 14th at 11 a.m. EDT. We wish to see you all in the next webinar. Thank you.